So exercise related to circuit questions and the answer with an answer key. So you will find the answer for each question at the end. We did the first 7 questions from this exercise. So I will start with question 8. So question 8, figure 10.1 shows a part of a circuit of a hair dryer, and that is working at 240 volts AC. The switch can be in one of 3 positions. It can be at A. So when it is at A, nothing is connected. You can see a circuit is open, no current, so all will be off. Or it can be at B, like we can move this to position B. So when we move to position B, what will the path? It's an AC, so you can take any of them as positive, as it will continuously change. So this will be the path, so only it will pass through X. So when it will pass through X, only one resistor or a heating coil is there as a part of a circuit. That's why there is a low or small amount of heat energy is there. Then if it can be connected to position C, when we connect to position C, more heating elements are there in the as a part of a circuit. So as a result, it will produce greater amount of heat energy. So it will have a high heater power. And it's a 240 volts AC supply is there. So if we have in the first part, all 3 heaters, X, Y, and Z, they have the power of 1000 watt. So each is having a power of 1000 watt. Heater Y and Z have equal resistance. Calculate the resistance of heater X. So how we can work out the resistance of heater X? So first, when it is connected here, we have the heater X and the power supply, they are parallel to each other. So if they're parallel to each other, if we have a 240 volt supply, this will be 240. It will receive the same voltage because it is parallel to the supply. When it is parallel, the voltage will be same. So we have the voltage. We will use a formula P is equals to VI first to get the current. And after getting a current, we'll use a formula resistance is ratio between voltage and current. We'll find the resistance. So P equals VI. P is the power of the heater, which is 1000. V is the voltage, which is 240, and I is the current. First, we'll find the current. So it will be 1000 divided by 240. What is the answer? 1000 divided by 240?
4.166.
So we have the current, that is 4.166 ampere. Now we have the current, we need the resistance. So if we need the resistance is a ratio between voltage and current. Voltage is 240 and the current is 4.166. When we divide, we'll get the resistance. So 240 divided by 4.166.
57.6.
So the answer is 57.6. And the unit of resistance is ohm. How we know it is 240 here? Because if you check, whenever the component is connected in parallel to the supply, it will receive the same voltage. It is 240, so this will receive 240. But for Y, so X is actually in parallel to the supply, that's why it receives the same voltage. But what happened to Y and Z? Y and Z have the equal resistance, so the voltage will divide between them. If it's a 240 volts, if they have the equal resistance, so voltage will divide. Equally, it will be 120 and 120. So voltage here is 120, voltage here is also 120. But X was the only component in parallel directly to the supply, that's why it received the same voltage. So when components are in parallel, the voltage is same. If they are in series, the voltage will divide. Is it clear, the first part, how we work out the resistance of X? First, we calculated the current, and from current, voltage divided by current, we get the resistance.
Yes, sir, clear.
What if X wasn't in parallel? So For example, yeah, it can be like this. Say we may have a circuit, because you can have a multiple possibilities are there for a circuit. For example, X, Y, and Z are all connected in series with each other. So if X, Y, and Z are all connected in series with each other, so what will happen if we say they are all identical? That is one thing, one condition. If they're all identical, then this voltage 240 will divide equally between them. So it will be 80 volts here, this will be 80 volts here, and this will be 80 volts here, as they are all in series. So, and what if all were in parallel? For example, if the same question was there and they say that these all resistors are in, or heating elements are in parallel to each other. So in that case, they will all receive the same voltage, that is 240 will be there across each of them. So this will be 240, this will be 240, this will be 240. And there is also another possibility that two of them might be in parallel and one is in series. That is another possibility, like because circuit may have different combinations. So there might be two in parallel and one in series to them. So in that case, the two parallel will not have 240. They will have the same voltage, but the total, like if this is 240, maybe, for example, if this was say 80. So this is 80, this will also be 80, because they are in parallel, but remaining voltage will be across this one. So it will be 160. So because these two are in parallel to each other, but not parallel to the battery, as there is another resistor next to them. So the combination will decide how the voltage will divide between the component. If all are in series, the voltage will divide. All are parallel, voltage will divide, voltage will be same. But if like one combination in parallel and next is series, so parallel will have same voltage, series will have the remaining voltage. And the total sum, when we sum 80 plus 120, 160, that will be 240. Then we have to calculate the resistance of heater Y. So how we can calculate the resistance of heater Y? So
voltage divided by current.
Yeah, voltage divided by current, but first we have to find what is the current there. Like example, 240 volt supply, so this will be 120. Why I say 120? Because they mentioned that they're identical. Y and Z have equal resistance. So if they have equal resistance, they will have the equal voltage as well. Equal voltage division. If they have different resistance in series, the one which is having a high resistance will have more voltage. So if it's a 240 volt supply, 120 here, 120 here. So we have the voltage. To get the resistance, it is voltage divided by current. We have the voltage which is 120, but we need a current. And how to find the current? Again, we'll use a formula P equals VI, where power is equals to 1000, voltage is 120, and current is I. This will go there in division. So 1000 divided by 120. So 1000 divided by 120, what's the current?
8.33.
So 8.23 ampere. So we have 8.33. So 8.33 ampere. So 120 divided by 8.33. What's the answer? One 20 divided
14.4.
14.4 an ohm. This is the method which we use. Like we use two formulas, but there's also a formula which can directly be used. I did not use that because I want to explain the idea. I can use a formula which is direct formula which relate the power, resistance, and voltage. And that formula P is equals to V square over R. I can use that formula, but I did not use, just to explain the idea that first I get the current and then voltage divided by current, I get the resistance. So it won't make difference if I use a direct formula. If I indirectly first calculate the current and from current, I work out the resistance. Then the current in heater Z when switch is in position C. So we already did that because we calculated the current in Y. The current in Y will be same as current in Z. Why? Because they are in series. So when two components, if the current in Y we calculated that was 8.33 ampere. So how much current will be there in Z? That will also be 8.33 ampere because they are connected in series. So when two components are connected in series, they will receive the same, or the same amount of the charges, or flow of the charges will be same. X will be, yeah, X will be different. X is, because X is different resistor, X is in parallel the current. Yeah, if they ask to calculate, for example, if the question was, what is the question is not about calculating the current from the battery, calculate the current in heater Z, but what if the question was calculate the current from the battery and the circuit was like this, all are connected. So if you want to calculate the current, when it is at position B, the current is only through X. When it is at position C, the current is only through Y and Z. But what if there was another type of a circuit in which all were connected? So, and the question is how much current is coming from the battery. So what we will do in that case, we'll find the current which we calculated. It was, I think, 4.11. 3 was there in X, and we calculated the current here. So we calculated the current in both of them, and then we get the total, we just add them. If the question was calculate the total current from the battery, current in each branch we sum and we'll get the final result. Question 9 part A, the digital electronic is not there in your syllabus, so we'll skip that. Now this circuit, whenever any kind of resistors are connected in series, what we call that as a potential divider circuit. Potential divider circuits, they divide the voltage between the component, and the side where there's a high resistance will have more voltage. For example, if the resistance of a variable resistor is high, it will have more voltage. So in comparison, the voltage here will be less. And opposite will happen if the thermistor is having a high resistance, more voltage across thermistor, so less voltage will be there across the variable resistor. And for thermistor, this is a circuit symbol for a thermistor, and its resistance and temperature are inversely proportional. So if the temperature is high, its resistance is low. How you will know it's a potential divider circuit? When you find two or more resistors in series, this is called a potential divider circuit. That's it. When two resistors are in series, we call potential divider. The first part, we have to name the component X and Y. So what is X? X is a variable resistor. And what is Y? Y is a thermistor. The second part, the fuel for an engine needs to be warm in order for an engine to work. If the temperature of a fuel is below the working temperature, the LED emits light. The fuel is too cold and the LED emit light. State and explain what happened to a circuit as the temperature of a fuel increases. So first, why the LED is switched on? As we know, for a thermistor, this is a thermistor. For a thermistor, what happened? Its resistance is inversely proportional to temperature. So when the temperature is low, when we have a low temperature, what about the resistance of the thermistor is high? So resistance of a thermistor is high. So it will have more voltage across thermistor, and there is a light emitting diode or LED in parallel to thermistor. So there will be more voltage across LED as well because they are in parallel, or equal voltage will be there. So as a result, when the voltage is high, this LED will be on, it will emit out light. But as the engine is working, the temperature of the engine start to increase. So when the temperature of the engine start to increase, what happened to resistance of the thermistor? If the temperature increases, as the temperature of a resistor, so it will start to decrease. When the resistance start to decrease. So as a result, what will happen? There will be, as a resistance start to decrease, so voltage across thermistor will decrease, or voltage across light emitting diode or LED will also decrease because they are in parallel. So when the voltage across LED decreasing, eventually there will be like no voltage to light up this LED. So LED or indicator lamp will be off. So that's how this circuit is working. When it is cold, thermistor is having high resistance, more voltage across thermistor, LED was on. But when the temperature increase, resistance of thermistor decrease, less voltage across thermistor, so the LED will switch off. Is it clear, this part?
Yes, sir, clear.
Anyone having a doubt? So resistance and thermistor, like resistance and temperature of a thermistor are inversely proportional. Now we change the position. In a figure now 8.2, LED is now parallel to a component X, which is a variable resistor. The temperature of a Y increases from a value below TW to a value above, like temperature is increasing. Predict what happened to the circuit. Now, as the temperature is increasing, so as the temperature increase, what happened to resistance of the thermistor? That will decrease. So if a resistance of thermistor decrease, so there will be less voltage across thermistor. And because there is a series circuit, if one side we have less voltage, the other side will have more voltage. So there will be greater voltage across the variable resistor, or now variable resistor in parallel to LED. So more voltage across LED, and the LED will be switched on. So the state here, what will happen to the LED light emitting diode? The light emitting diode will be switched on. So as the temperature rise, we always take the direction of a conventional current. This, whenever you are explaining the working of a potential divider circuit, better explain in terms of the voltage rather than current. I can explain this. Yeah, I will explain the working of this. For example, see, when it was cold. So in terms of the current, I can explain the working of this as well. So what happened when it was cold? The temperature is low, so resistance is high. So this was having a high resistance. So how the current start to move? The conventional current, it will move from here. Because this is having a high resistance, so majority or most of the charges will flow through LED. As most of the charge will flow through LED, the light emitting diode will be on. This is in terms of current. And what happened? As the temperature start to increase, why the LED or a light emitting diode switched off? As the temperature start to increase, the resistance of a thermistor decreases. So as the resistance of the thermistor start to decrease, so most of the current will flow through the thermistor because it has a low resistance. So a very small amount of a current is an LED, and that is not sufficient to light up the LED. That's why the LED will be off. If the conventional current is coming from the side of the play like this, when it is coming from the side of the triangle, the conventional current, the LED allow that. If the current is coming from the side of the pause, then it will block. So if it is coming from this side, it will block. If it is coming from the side of a play, it allow that current. So same thing, this is, but better whenever you explain the working, explain in terms of voltage rather than current. Same thing happened here, like when the initially as the current start to flow, so this is having a high resistance, this is and when the temperature is there below, so most of the charge, like the temperature start to, as they mention here, the temperature increase, so resistance and temperature are inversely proportional. So as the temperature start to increase, resistance decreases. So if resistance decrease, there will be less voltage here. In comparison, more voltage more voltage across LDD and LED will be on. So in a potential divider circuits, if you have a potential divider circuit which might have variable resistor, thermistor, or light emitting diode, or LDR, light dependent resistor. So the simple rule is that the side where there is more resistance, that will have more voltage, and the side where there is low resistance, that will have less voltage. If one side voltage increase, the other side voltage will decrease in a potential divider circuits. Question 10. The resistance of a circuit component vary with the brightness of a light that falls on it. State the name of component. Which component the resistance changes with light? Which component, you can use your mic or a chat to state which component resistance changes with the light, that is known as thermistor is affected by temperature, and light dependent resistor or LDR is affected by light. Yeah, that's right, LDR or light dependent resistor. So, and then you have to draw the circuit symbol for a light dependent resistor. So this is a circuit symbol for LDR or light dependent resistor. Variable resistor is affected by like the three resistors which changes the like components which can change the resistance. There are three components which can change the resistance. One is a variable resistor, one is a thermistor, another one is, yeah, I will draw the structure of LDR as well. So one is a variable resistor. Another one is thermistor. And the third one, the component which changes its resistance, that is LDR, or also called a light dependent resistor. You can write LDR in exam, it's acceptable. The circuit symbol for variable resistor, this is a circuit symbol for variable resistor. How its resistance changes for a variable resistor, so how variable resistor, its resistance is directly proportional to length. So if we move the variable part, like if we move this part, if we change the position, the length will change. Like for example, if I say we have side A and B. So, or A, B, and B is representing, say, a movable part is B and this one is C. So if we are moving the position, so A and B length is increasing, it means the resistance will increase for AB, and B and C resistance decrease as the length is decreasing. So by changing the length of a wire, we change the resistance. But for a thermistor, what happened? This is a circuit symbol for a thermistor. Its resistance is inversely proportional to temperature. When the temperature is high, its resistance will be low, or other way around, if temperature is low, its resistance will be high. And the third one is a light dependent resistor. Its resistance changes with light. The arrows are pointing into, and its resistance and light intensity are inversely proportional. If we have like more light or more light energy, so if we have more light energy, the resistance of LDR will be low. Like daytime resistance is low, at night the resistance will be high. So these are the components which resistance changes. For a variable resistor, if we change length, resistance change. For thermistor, if we change temperature, resistance changes. For a light dependent resistor, if we change the light intensity, the resistance will change as well. So here we have to draw. So here we have to draw the circuit symbol for the thermistor. So how we draw a circuit symbol for thermistor? LDR, not thermistor. So we'll draw a rectangular box. the two wires which are coming out, and then the arrows are pointing in. The next one, figure 9.1, shows a 6-volt battery is there, which is connected to 1.2 kilo ohm resistor and a thermistor. At a certain temperature, resistance of a thermistor is 2.4 kilo ohm. So this is 2.4 kilo ohm. Calculate the reading on the voltmeter. Look, this is a potential divider circuit as well, because two different type of resistors are connected in series. So this is a potential divider. What actually we'll do, we'll find the voltage across the thermistor, and voltage across the thermistor will be same as voltage of the supply. And for that, whenever two resistors are connected in series, we call that circuit as a potential divider circuit. And to work out the voltage of a potential divider circuits, any type of resistors are there which are connected in series. The first resistor we call R1 and the second resistor we call R2. The voltage of a supply, this is the formula for potential divider circuits. Potential divider circuits are also known as series circuits. So if we have two resistors, one is R1, another one is R2. So if I need the voltage here, if I need the voltage across the first component, the formula is that V1. If I need voltage across the first component, so if I need this one, so V1 is equals to resistance of that part divided by the sum of the resistance into total voltage V. That's a formula to get the voltage across the first component. If I need the voltage across the second component, that is V2 equals to resistance of that part divided by the sum of the resistance of two component multiplied by total voltage V. So the previous question, as you can see, it is a potential divider circuit. So we have two resistors. One is 1.2 kilo ohm, or you can also say 1200. Another one is 2.4 kilo ohm. Even without calculation, you can find that 2.4 will have more voltage as it's a high resistance in series. Now, if I need the voltage here, if I say voltage here is V1 and voltage here is V2. So if I need V2, V2 is equals to resistance of that part divided by the sum of the resistance of the two components which are in series and multiplied by total voltage of a circuit, which is V. So we just substitute the value. It is 2.4 kilo ohm. 2.4 kilo ohm will convert into ohm, which is 2400 multiplied by 1000 divided by sum of the resistance. This is 1.2 kilo ohm, so it will be 1200 plus 2400 into combined voltage, the total voltage, that is 6. So when you simplify, this will be 2400 divided by 3600 into 6. So what's the answer? This will be 4. So means, okay, 4. So this will have 4 volt. So if this is having 4 volt, what is the reading on the voltmeter? That will also be 4 because they are in parallel to each other. So what is the voltage across the thermistor? The same voltage will be there across the other component as they're in parallel. And what about the voltage across 1.2? If total is 6 and 4 volts here, so remaining 2 volts will be across 1.2 because the voltage will divide between the components. Is it clear, this one?
Yes, sir, clear.
The battery connected to figure 9.1 is not changed, suggests the change that would cause the reading of a voltmeter to decrease. Like we did not change the battery. We want the voltage here to decrease. It's a thermistor here. So what I want resistance to increase. If I need a voltage to decrease, what I want? Resistance to increase, decrease. If I need less voltage. So I need R to decrease. And how R can, yeah, that's right, how R can be decreased for a thermistor, because resistance and temperature of a thermistor are inversely proportional. If I want, yeah, so I should increase the temperature. So when we increase the temperature, the resistance start to decrease. Another question, figure 8.1 shows a 12-volt supply is there, and this is a movable part. So look, when the conventional current or any kind of current is there, even electron flow you take, so this is how the current will flow. So how this combination will appear, it appears that they are in series because there's only one passage for the charges to flow. So if there's a 12-volt supply, and if I say there's a 6-volt here, how much voltage will be there between A and X? So what will the voltage across A and X? That will be 6 as well, because in series the voltage divide. But if I say I have a 12-volt supply and there's a 8-volt across the lamp, how much voltage will be here? So how much voltage will drop across A and X? So remaining, so that will be equals to 4 volts. The total should be 12 in series. Whenever combinations are there in series, the total voltage divide between the components. So if it's a total 12 and here I have 8, so remaining 4 volts will be here. So we can change the brightness of the lamp by moving this sliding contact. When this sliding contact is moved here, when we move this sliding contact from more towards B, so as a result, when we move towards B, so here the length increase, so resistance will also increase. If a resistance increase, so there will be more voltage across this component and less voltage across the lamp, so the brightness of the lamp will decrease. The circuit include a lamp and a resistance wire AB with a cross-sectional area. There is a sliding contact. The rating of a lamp is having a voltage 6 and a power 9. The current, if we have the voltage and power, how to find the current? You have to learn the formulas in electricity. If you have voltage and power, so we can find the current using a formula P equals VI. So P is equals to VI, where P is the power, which is 9. V is the voltage, that is 6, and I is the current. So 6 is multiplied, other side will be divided, so it will be 9 divided by 6, which is equals to 1.5. So 1.5 and the unit is ampere, so it will be 1.5 ampere. Whenever you're solving a question, 1 mark is for either substituting a value in formula or writing a formula. So it's better write a formula first. Then we need the resistance. So to get the resistance is a ratio between voltage and current. So voltage, we already know it's 6, and the current we calculated in the previous part, that was 1.5. So it will be 6 divided by 1.5. So it's equals to 4, and the unit of the resistance is ohm. So it is equals to 4 ohm, or you can also write omega. The AB is having a length of like AB is of 1 meter and has a resistance of 5 ohm. Like this total from A to B, the length from A to B is 1 meter, and the total resistance of this one is 5. The lamp has a normal brightness when a sliding contact is at X. The sliding contact is moved to B. Without calculation, why the lamp become dimmer? You don't have to do calculation. You just have to tell why the lamp will become dimmer. If you move this sliding contact towards B, so as a result, what will happen? The resistance of the AB will like in the beginning. See, when it was exactly at the center, we were using only this total wire A and B is having a length of 5, but A and X is having a length of 2.5. Only half of the wire is used, so that was having a length of 2.5. So, but what happened when we move the sliding contact more towards B? If this sliding contact is moved towards B, the length of a wire increases. So as the length of a wire increases, so resistance of a wire which we are using will also increase. As the resistance increase, there will be more voltage across AB and there is less voltage across the lamp. That's why the lamp will become dim. Then calculate the distance AX for a lamp which have a normal brightness. Okay. So if it is having a normal brightness, look, why it get dimmer? See, the part of a this from A to B, the total length of A and B is 1 meter, and we were using a part of it. So we are not using full, we are using a part of it. Like example, say half of it we were using. So what is the resistance of half? That is 2.5. So if resistance is 2.5 here, there will be less voltage, maybe out of 12, maybe 4 volts here, or remaining, or maybe 6 volts here, and remaining 6 volts was across the lamp. So the lamp was normal at a normal brightness. But now what we did, we moved the sliding contact from X to B. So when we move the sliding contact from X to B, the length of a wire which we are using has increased, because first from A to X it was low resistance, but from A to B that resistance is 5 ohm. That is more resistance. As a result, when the resistance increase, more voltage across this wire, or out of 12 maybe it will have 8 volts. So remaining 4 volts will be across the lamp, so the brightness of the lamp decreases. Is it clear?
Yes, sir, clear.
Then the next part, we have to calculate the distance A and X for a lamp to have a normal brightness. So if we want, like we want this length, how long is this? Look, if a lamp is having a normal brightness, this is 6 volts and this will also be, no, in the figure it is showing a half. We want to calculate exact value of it. In the figure, it looks like it is exactly half, but we have to calculate, like show by calculation. About less than a minute left, so I'll share another link and explain this.